Hi guys. So I'm going to finish the Cartier Operator arguments. So here's the theorem. So let X over S be a smooth scheme. So this is a smooth scheme where S is spec K, and K is a perfect field of characteristic P. I don't think the perfect is really that essential. So there exists an isomorphism of OX to the P modules. Okay, you don't really need to use OX to the P modules here. You could use like a semi-linear construction, but we'll relativize it. So here, let's say from I below to I. So then I'm going to characterize now, after I write this down, the map. So this is the inverse of the Cartier operator. Satisfying, so this is the characterization. Three properties. One is that it takes 1 to 1. Two, so it's multiplicative, let's say, of okay, so this is for all eta and C. X to the P over S. So I guess what I could have done here is, so this is kind of means that they're a system together. Instead of here, I could have put bullets here and then said something about graded rings, and so this would make it a graded ring map. Okay, and so here the last one is just like how we define it on the first part. So on 1. Okay, and so this is f to the P minus 1 df, like so. Okay, so then I've twisted it, and then you do this. Okay, so this is the Cartier map. This is the theorem that we want to prove. So basically, we've already done all the work. So this is Cartier's theorem. So proof. Okay, so we first claim so that the construction for all the i's can be reduced to the case I is equal to 1. Okay, so how do we do this? So for I is equal to 0, this is handled by the first condition, and for I is greater than 0, this is handled by the second condition. So multiplicativity for the definition. Okay, so for the definition, we're just gonna have this one and this one. Okay. Okay. So the question. These two conditions. Okay. So the construction is reduced to the case I is equal to 1. Okay. So the question of isomorphism. Okay. So now I'm going to continue. I'm going to talk about isomorphisms here. So the question of isomorphism is local, so you can check epimorphisms and monomorphisms of sheaves of quasi-coherent modules on the stocks, or just all sheaves can be checked at the stocks. Okay, so this is really a local question. Okay, so now we're going to do this. We're going to reduce to this affine space. Okay, so let me continue this. So proof. Okay, so if X is smooth, S is, oh sorry. So what do I need to say? I need to say since X over S is smooth, yeah. smooth, there exists a cover, let's see, by affine opens, cover by affine opens, with tall maps, epsilon j from uj to affine space. Okay, let's say that n is the dimension of x. Okay, so we have a tall maps like this, and so what does this tell us? This tells us that by the tall property. Okay, so it says that for all j, we have the following. It says that omega uj over si. So this is isomorphic to epsilon j star of omega I a n s over s. Okay, so here this is really affine space. Okay, so then there's two things that this implies. Okay, the first thing that it says is that so this is an affine, f is an affine map, so f lower star of uj over s I is isomorphic to f lower star of epsilon j here, this pullback by here over s. Okay, the second thing that it implied is that the twists, so that, okay, if you have an atoll map, that the Frobenius twist is still atoll. Okay, so okay, and the p over s. So these both have subscripts s here. Okay, so we have these two things. So this is nice because here in the theorem we just need to check the two sides here. So this was the first thing that I did, and then here this is the second thing. And so both of these things locally will reduce to affine space. Okay, so maybe I should have said something else, that this is functorial. So there's a functorial. Okay, so it's functorial because this definition here respects ring homomorphisms. Okay. Okay, so then this allows us to reduce the whole proof to affine space. Okay, so so this implies proof reduces to the case S, which we already proved. Okay, and that's that. So that pretty much sums up the Cartier operator, the basic part. There's some other business about the Cartier operator on de Rham cohomology in this Hasse-Witt matrix, Hasse-Witt matrix. If I need that, I'll get into it, but this is what we have for now. So thanks for watching. If you like the video, let me know.